I'm going to solve another West African Senior School Certificate Examination Physics Practical. The aim of this experiment is to determine the acceleration due to gravity on Earth using a helical spring. Without wasting time, let's get right into it. You have been provided with a retort stand. A helical spring, a meter rule, set of masses, plasticine, a stopwatch, and other necessary materials. We are going to set up the apparatus as shown in this diagram. This is the retort stand, this is the meter rule, this is the helical spring, and we have our pointer here with some plasticine holding the pointer. We are going to hang some mass here on the hanger. So we are going to set the mass to 200 grams. This is 100 grams together with the hanger. So we add another 100 grams to it, making 200 grams. Then we hang it on the hanger. We are going to read and record the pointer position on the meter rule. The pointer position is 20 centimeters. We are going to add a mass of 50 grams to the hanger. Each of these mass is 25 grams, so we add the two of them, making 50 grams. We are going to read and record a new pointer position on the meter rule. The new pointer position is 22 centimeters. And now we are going to determine the extension, that is L minus L naught. L is 22 centimeters minus L naught, which is 20 centimeters. So we have 2 centimeters as tension. And we are going to convert the extension from centimeters to meters. We can convert it to meters by dividing by 100. So we have 2 divided by 100, and the chain is now 0.02 meters. We are going to displace this mass downwards and release it to perform vertical oscillations. And then we read and record the time for 20 complete oscillations. So when we displace this mass downwards and release it, it will move up and then come down. and that will be counted as one oscillation. We are counting 20 oscillations. So when we release it, we will start the stopwatch and count 20 oscillations. On the 20th count, we stop the stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 13.12 seconds. We are going to repeat the 20 oscillations again for more accurate results. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 13.22 seconds. So for a mass of 50 grams, the extension was 0.02, and then the time for 20 oscillations, we have 13.12, and then the second one is 13.22. We are going to find the average of the two times. So we add 13.12 to 13.22 and divide the results by 2. So we have 13.17 seconds. Remember, the mass is in grams, the extension is in meters, and then the time for 20 oscillations is in seconds. And we are going to determine the period and then evaluate the period square. For the period, we are going to divide the average time by 20. So we have 13.17 divided by 20, which is 0.659. And we are going to square 0.659. We have 0.43. And we are going to repeat the procedure for a mass of 100 grams, 150 grams, 200 grams, and then 250 grams. In each case, we are going to evaluate the period and square the period. So we change the mass to 100 grams. Remember that the 200 is constant. Remember this 200 is kept constant. So we are going to change this mass to 100 grams and determine the extension in meters. And then record the time for 20 oscillations. Repeat it. Find the average of the two times. Find the period and then square the period. And we do the same thing for a mass of 150 grams, 200 grams, 250 grams, and then tabulate the results. Now we are going to plot a graph with t-squared on the vertical axis and e on the horizontal axis. So we need the values of t-squared, and they are decimals. We can easily convert them to standard form by removing this point 1, 2 to the right. So we have 43 here. times 10 exponent negative 2 and the unit is second square. We move this point to 1, 2 and we have 51. The next one is 59, 67 and then 75. All times 10 exponent negative 2 in standard form. We also need the values of the extension E. So we move the point 1, 2 and we have 2 over here times 10 exponent negative 2 and the unit is meters. We move the point 1, 2 over here 2 and we have 4. The next one is 6, the next one is 8 and the last one is 10. All times 10 exponent negative 2 meters. So we are going to plot these values on the graph with t square on the vertical axis and the extension E on the horizontal axis. So we draw our vertical and horizontal axis. And we are plotting a graph with t squared on the vertical axis and E on the horizontal axis. So we are going to choose a scale. We choose a scale of 2 centimeters is to 10 times 10 exponent negative 2 second square on the t square axis. So we start from 0, 10, 20 and so on the vertical axis. And here we start with 1, 2, 3, 4, 5 and so on. On the vertical axis, one big box is 10. When we divide by 10, it means one small box is going to be 1. And on the horizontal axis, one big box is 1. 1 divided by 10 is 0.1. So each small box on the horizontal axis is 0.1. So we start plotting. For the first value, we have 2 on the horizontal axis and 43 on the vertical axis. So this is 2 and this is 40. We count 3 boxes and put the point there. The next one, we have 4 on the horizontal axis and 51 on the vertical axis. This is 50, so one more box will make it 51. The next one, 6 here and 59. So we have 50, we count 9 boxes. The next one, we have 8 here, 67 on the vertical. This is 60, we count 7 more boxes. The last one, we have 10 here and 75. This is 70, so 75 will be in the middle here. And then we draw the line of best fit. Determine the slope S of the graph. So we draw a horizontal and a vertical line. And name here A, here B, and here C. The slope is given by change in BC divided by change in AB. For change in BC, we have 63 minus 45. Remember, times 10 exponent negative 2 and the unit is second square. And for change in AB, we have 7 minus 2.5, also times 10 exponent negative 2, the unit is meters. So times 10 exponent negative 2 will cancel out, and 63 minus 45 is 18. The unit is second square. 7 minus 2.5 is 4.5. The unit is meters. And 18 divided by 4.5 is 4. We have second square at the numerator, and the denominator is meters. So when we reciprocate it, we have per meters. We are going to evaluate k is equal to 4 pi squared over the slope. Pi is 3.142 and the slope is 4 seconds square per meter. So we replace them, and then 4 will cancel out, and the only value left is 3.142 square, which is 9.87. And then the reciprocal of per meter is meter, and the reciprocal of second square is per second square.